It was politician, businessman, and television personality Morton Schulman who said, "To make a million, start with 900,000. In this lesson, we're going to understand the derivation of the compound interest formula, and we're going to make computations using the compound interest formula. All to answer the question, what are the advantages of using the compound interest formula? Before we jump into it, let's make sure we're ready for this by doing warm-up number 2. Let's factor x squared minus x minus 20. When factored, we find that this becomes x plus 4 times x minus 5. Now, let's factor x squared minus 9x plus 20. When factored, we get x minus 4 times x minus 5. And finally, let's factor x squared plus x minus 20. From that, we get x minus 4 times x plus 5. We can see how changing these signs dramatically changes the polynomial that we'll get. Now, let's take a look at a problem that you will be able to do by the end of this lesson. Sharon deposits $8,000 in a 1-year CD at 2% interest compound daily. What is Sharon's annual percentage yield to the nearest hundredth of a percent? So, to find the annual percentage yield using the compound interest formula and the simple interest formula, first let's find out what happens under the compound interest. So B is 8,000 times 1 plus 0.02 divided by 365 to the 365 times 1 power. This will give us a B value of $8,161.61. Now, we're going to take a look at the simple interest formula and subtract the principal amount from the ending amount, the balance from the first equation. Means that the interest that was earned was $161.61. We know that the principal amount was $8,000, and we know that the rate was 0.02. So this would mean that the rate would be equal to the interest earned divided by the principal times the number of years. Or that the rate is equal to 161.61 divided by 8,000 times 1. Meaning that the annual percentage yield rate would be 0.0202, or 2.02%. Or another way we could do it is by using an annual percentage yield formula, where the annual percentage yield is equal to 1 plus r over n to the n power, and then minus 1. We substitute the values into the equation, and we find an annual percentage yield of 0.0202, which is still 2.02%. Julio deposited $10,000 in a 5-year CD with the intention of using the money for his son's college education. The account pays 2.2% interest compound daily. There will be no deposits or withdrawals during the 5 years. Julio wants to know what the $10,000 will grow to by the end of 5 years. Imagine if he sets up a daily compound interest table as in the last lesson. There are over 1,800 days in 5 years, so the table would get quite tedious. It is not practical to solve this problem one day at a time. Calculating compound interest using the simple interest formula is tedious when there are numerous periods. Power of mathematics can turn the long procedure into a relatively small amount of work. Numerical examples and algebra can be combined to uncover the pattern that leads to a formula that finds compound interest. The compound interest formula relates principal, interest, rate, and the number of times interest is compound per year, and the number of years the money will be deposited to find the end balance. The formula is used for any type of compounding annually, semi-annually, monthly, weekly, daily, and so on. In the lesson on savings accounts, we used annual percentage rates, or APR, to compute interest. Most banks advertise an annual percentage yield, or APY, since it is a higher number than APR for accounts compounded more than once per year. The bank takes the dollar amount of interest you can earn under compounding to create the APY. The APY is the simple interest rate that would be required to give the same dollar amount of interest that the compounding gave. Therefore, APY is an annual rate of interest that takes into account the effect of compounding. Here, we will solve some compound interest problems and then look for a pattern to derive the compound interest formula. Joe opens a savings account with principal P that pays 2% interest compound quarterly. What will his end balance be after 1 year? Let's start by using the simple interest formula where I equals PRT. This means we're going to wind up with whatever that principal amount of money is times 0.02, the interest rate as a decimal, and 1 over 4 because it compounds quarterly. Now we're going to let B1 represent the first quarter's ending balance and the sum of P and the first quarter's interest. So P plus P times 0.02 times 1/4. We can factor out the P to get P times 1 plus 0.02 over 4. And this 0.02 over 4 is me just combining the 0.02 and the 1/4. To get the second quarter's ending balance, follow the same procedure with a new balance of B2. Now B2 is equal to B1 times 1 plus 0.02 over 4. Let's remember that B1 is in fact P times 1 plus 0.02 over 4. With that B replaced, we now put that parenthesis term 1 plus 0.02 over 4. We can notice the repeating terms within the parentheses, meaning we can write this in a more compact form to say P times 1 plus 0.02 over 4 squared. To find B3, we repeat the process, replacing what used to be B1 with B2. We factor out that B2 so that it is B2 times a very familiar parenthesis. Replace the value of B2 with what we found to be B2 previously, and then copy down the parenthesis we have remaining. And because both of these are the same, we have an invisible one, meaning we have 2 of the parentheses, and 1 of the parentheses, meaning we have 3 of them. So if I wanted to find B4, I should be able to say that that is the principal amount times 1 plus 0.02 over 4 to the 4th power. Let's check our understanding of this. Rico deposits $800 at 1.87% interest, compound quarterly. What is the ending balance after 1 year? And we're going to round this to the nearest cents. Now we already know the formula from the previous example where B4 is P times 1 plus the interest rate of 0.0187 divided by 4 to the 4th power. Now, to make sure we do this correctly on a TI-30XA, we need to make sure we follow the order of operations correctly, starting innermost in the parentheses with 0.0187 divide 4 equals, plus 1 equals, exponent 4 equals, times 800 equals. And we get $815.07 because we're rounding to the nearest cent. Now let's understand how the compound interest formula is derived. If you deposit P dollars for 1 year at 2.3% compound daily, express the ending balance algebraically. We know our formula from example 1, so we go ahead and start by having that. This would mean that B sub 4 will be equal to P times 1 plus the interest rate of 2.3% is 0.023. Daily means 365 times in a year unless it's a leap year, and then 365 as the exponent. Let's check our understanding. If Nancy deposits $1,200 into an account that pays 1.7% interest, compound monthly, what is her ending balance after 1 year? And we're going to round this to the nearest cent. So we start with our formula once again, and we can just fill in some values where $1,200 is her principal amount. So 1 plus an interest rate of 1.7 is 0.017 divided by 12 for monthly, and raise this to the 12th power. So to do this, we're going to say 0.017 divide 12 equals plus 1 equals exponent 12 equals times 1,200, and we're going to get $1,220.56 because we're rounding to the nearest cent. Let's extend our understanding further and say Nancy receives 2 offers in the mail from other banks. One account offers 1.38% compound daily, the other offers 1.9% compound quarterly. Would either of these accounts provide Nancy with a better return than her current account? If so, which account? We know at 1.7% monthly, she's going to have $1,220.56 in her account. So we set up the balance for 365 days using 365 and the interest rate as both the numerator, the denominator, and the exponent. This means in 365 days compound daily, she will have $1,216.67, which means this is not a better deal than her 1.7% monthly. If we set up the equation for when it's done quarterly, the first thing to draw your attention to is we're using the subtext to indicate whether it's compound daily or quarterly. By calculating the quarterly, we get $1,222.96, which means this one is best. The first two examples involved accounts for 1 year. The exponent and the denominator in those formulas were the number of times the interest is compounded in 1 year. You can obviously leave your money in an account for more than a year. The formula used to compute the ending balance indicates the variable t, where t is the number of years. Here on screen, we can see the compound interest formula, where B is the ending balance, P is the principal or the original balance, R is the interest rate expressed as a decimal, N is the number of times interest is compound annually, and T is the number of years. Now let's make computations using the compound interest formula. Mary deposits $1,650 for 3 years at 1% interest compound daily. What is her ending balance? The first thing we want to do is identify those variables. So her principal amount is $1,650, and her interest rate is 1% expressed as a decimal, where the number of times it compounds is 365, and that'll be for 3 years. So the formula will read B is equal to 1650 times 1 plus 0.01 over 365 to the 365 times 3 power. So to put this into a calculator, we're going to go 0.01 divide 365 equals plus 1 equals the exponent button, open the parentheses, 365 times 3, close the parentheses, equals, times 1650 equals, and we're going to get 1,725 cents. Let's check our understanding of this, and Kate deposits $2,350 into an account that earns interest at 1.1% compound monthly. What is her ending balance after 5 years and round to the nearest cent? Let's identify the variables where P is $2,350, R is 0.011, N is 12, and T is 5. So we set up our equation substituting in the values for all of the variables. To simplify some of this for us, we can say that 12 times 5 is 60. So we can look at the exponent as simply being 60. This would mean 0.011 divide 12 equals plus 1 equals exponent button 60 equals times 2350 equals, and we will get 2482.81. Now let's extend our understanding of this and write an algebraic expression with the ending balance after K years for an account that starts with a balance of $2,000 and earns an interest rate of 1.5% compound daily. The first thing to do is to write out our equation and to get ready to fill in the variable values. P is 2,000. The rate is 0.015. The number of times per year is 365, but the time frame is unknown as K. So B would be equal to 2,000 times 1 plus 0.015 over 365 to the 365 times K exponent. Sharon deposits $8,000 in a 1-year CD at 2% interest compound daily. What is Sharon's annual percentage yield to the nearest hundredth of a percent? So, to find the annual percentage yield, using the compound interest formula and the simple interest formula. First, let's find out what happens under the compound interest. So, B is 8,000 times 1 plus 0.02 divided by 365 to the 365 times 1 power. This will give us a B value of $8,161.61. Now we're going to take a look at the simple interest formula and subtract the principal amount from the ending amount, the balance from the first equation. Means that the interest that was earned was $161.61. We know that the principal amount was $8,000, and we know that the rate was 0.02. So this would mean that the rate would be equal to the interest earned divided by the principal times the number of years. Or that the rate is equal to 161.61 divided by 8,000 times 1. Meaning that the annual percentage yield rate would be 0.0202, or 2.02%. Or another way we could do it is by using an annual percentage yield formula, where the annual percentage yield is equal to 1 plus r over n to the n power, and then minus 1. We substitute the values into the equation, and we find an annual percentage yield of 0.0202, which is still 2.02%. Let's check our understanding of this. Barbara deposits $3,000 in a one-year CD at 1.1% interest, compound daily. What is the annual percentage yield to the nearest hundredth of a percent? We already know that the annual percentage yield is the sum of 1 and r over n to the n power minus 1. This means that we can substitute all of our values into our original equation, and we get 0.01106, which means we get 1.11%. Let's extend our understanding of this and consider the amount X deposited into a CD at 2.04% interest compound daily, and the same amount deposited into a CD at the same rate that compounds monthly. Explain why after 1 year the balance of a CD that compounds daily is greater than the CD that compounds monthly. In both cases, we're going to set up an equation just to have the variables. You're going to see I use the subtext 12 or 365 to refer to which one we have. Looking at the monthly, we get 1 plus 0.0204 divided by 12 to the 12 power minus 1, which gives us an annual percentage yield of 2.059%. Looking at the daily, we get 1 plus 0.0204 divided by 365 to the 365 power minus 1, or an annual percentage yield for the daily compounding of 2.06%. So why does the daily have a higher percentage? Simple, because it compounds more frequently.